In the last class, we discussed the postulates of quantum mechanics. We discussed the solution of hydrogen atom, the solution of Schrodinger equation. We saw the solution of Schrodinger equation gave the wave functions, and these wave functions can be described in terms of some quantum numbers. We discussed about two quantum numbers, the principal quantum number and the azimuthal quantum number or the orbital quantum number. In today's class, we will continue our discussion and we will talk about the remaining quantum numbers. The next quantum number that we will discuss will be magnetic quantum number. The magnetic quantum number. Which is signified with letter M. Now, what is we saw that principal quantum number n talked about the size, azimuthal quantum number talked about the shape, and magnetic quantum number talks about the orientation of this orbital. And at the moment we will say that this orientation, by this orientation we mean orientation in space. What kind of orientation does it have? So, this signifies the orientation of the orbital. We saw that the value of L, the azimuthal quantum number, was determined by the value of n, the principal quantum number, that was the leading quantum number, and then was the azimuthal quantum number. Now, the value of magnetic quantum number m, so value of m is decided by, depends on the value of L. So, what values of L have we seen? We have seen L is 0. When L is 0, it is s orbital. When L or L is 1, then it is p orbital. L is 2, this is d orbital. L is 3, this is f of orbital, and so on and so forth. Now, when L is 0, it is s orbital and the shape is sphere. Let us say I draw my x axis, y axis, z axis, and I am showing you a sphere. So, how many ways can I orient this sphere? The answer is 1. There is nothing called reorienting the sphere because it is symmetric along all direction. So, there is only one way then that this s orbital can be oriented. So, the number of ways that this can orient is 1. So, this is number of orientations possible. For s orbital it is 1. What about p orbital? P orbital looks like a dumbbell. So, it has got two lobes. So, if I draw my Cartesian axis, I can have this as x, this as y, and the plane above and below the plane of the axis above and below the plane of paper, let us call that z. So, you see that the way I have drawn this particular dumbbell, it is oriented along y axis, but I can orient, I can twist it by 90 degree and then reorient it along x axis. So, this is my y, this is x, and this is the z axis. So, this is another orientation, and then I can also orient along z axis, which is above and below the plane. So, this is the z axis. So, I can orient it in this way. So, this lobe actually goes below the plane of the paper. So, you saw I can orient this p orbital in 3 different ways, either along y axis or this one along x axis or this one along z axis. So, I have got now 3 orientations. This number of orientation for p orbital is 3. Now, similarly, d orbital actually has a double dumbbell shape. Let us draw this way. It has got two different dumbbells, and I can reorient it in 5 different ways. I am not trying to draw that. You see, these are 5 different orientations that these d orbitals can show. So, you see that in this picture the two dumbbells. So, this is one dumbbell in silver color, another in orange color. Both the dumbbells are actually on the xy plane. So, this is z is going coming out of the plane of paper, and these dumbbells are actually on the xy plane. So, I call that dxy, or I can also arrange the dumbbells along the xz plane, or I can arrange these dumbbells along yz plane, or along the in all these three cases you saw actually the dumbbells, the lobes of these dumbbells were actually within the two axes, or I can. So, these three are within the axis, the lobes are within the axis, and the remaining are actually on the axis. In this case you see the dumbbell, the lobes are on x axis and y axis, and this is slightly difficult to explain because it is a linear combination of two different orientations, but we see that there are 5 different possible orientations for d orbitals. So, for d orbitals number of orientations that are possible are 5. So, what we see here, the s orbitals can be oriented only in one way because it has spherical symmetry. The p orbitals can be oriented either along x axis, y axis or z axis, we call them px, py, pz, or the d orbitals can be arranged in 5 different ways called dxy, dxz, dyz. This is called dx square minus y square. So, this is dxy, dxz, dyz, dx square minus y square, dz square. So, there are 5 different ways that the d orbitals can orient. So, this magnetic quantum number tells what is the orientation of the orbital that I am interested in. When L is 3, it is very difficult to even drive point by showing a beautiful illustration. We will skip that part, and I just tell you that there are 7 different ways to reorient this L equals 3, which is the f orbital. Right. So, what did we see so far? We saw that s orbitals can be oriented in one way, p orbital can be oriented in 3 different ways, we call them px, py, pz. D orbitals can be oriented in 5 different ways, dxy, dyz, dzx, dx square minus y square, dz square, these 5 ways, and f orbitals can be arranged in 7 different orientations. So, you see for a given value we can actually generalize this. For a given value of L, so because this S, P, D, F they signify a particular value of L, for a given value of L there are 2 L plus 1 orientations possible. And what are these values of the 2 L plus 1 orientation? They go from minus L to plus L in the step of 1. So, minus L, then minus L plus 1 and then L minus 1 and L. So, there are 2 different, so in between the 0 will come. So, there are this way there are 2 L plus 1 different orientations starting from minus L to plus L. So, let us say our L is here I give the value of L, let us say L is 0. So, how many number of orientations given by 2 L plus 1? So, 2 L plus 1 is 1 because L is 0, and what are the values? So, it goes from minus L to plus L via 0. What is my L? 0. So, minus L is 0, plus L is 0. So, we got only one value. So, this is the value of the magnetic quantum number m. When L is 1, how many possible values are there? 2 L plus 1 is 3, and what are they? It starts from minus L, that is minus 1. In a step of 1, minus 1 plus 1 is 0, and one more step, minus 0 plus 1 is plus 1. So, it can be minus 1, 0, plus 1. These are the 3 different magnetic quantum numbers. When L is 2, how many different orientations are possible? That is 5. 2 L plus 1 is 5. What are they? They are minus 2, minus 1, 0, plus 1, plus 2, and so on. When it is 3, there are 7 different ways and they go from -3 to +3, 7 different ways. When it is L is 0, we just call it S. When L is 1, we call them P x or P y or P z, but please note that there is no direct correspondence of, you cannot say that -1 belongs to P x or 0 corresponds to P y or +1 corresponds to P z. They have a relation, but their relation is slightly complicated. So, we will be happy if we know this much, that for L equals 1, there are 3 different orientations, their magnetic quantum numbers are -1, 0, +1, and we call them P x, P y, P z. We will not try to direct provide a one-to-one correlation between them. And similarly, when L equals 2, we have d x y, d y z, d z x, d x square minus y square, d z square, and F will have 7 different. Let us look at this example. Let us say my n value is 3. The task is find out the number of orbitals, right. So, when n is 3, what are the possible values of L? L can be 0. So, there are, since n is 3, there are 3 possible values of L, and they are 0, 1, 2. So, it goes from 0 to n minus 1, all right. When L is 0, what do we call it? We call it 3s, and when L is 1 and n is 3, what do we call it? It is 3p. When n is 3 and L is 2, we call it 3d. So, this orbital notation identifies the principal quantum number and azimuthal quantum number, but we know that is not the end of the story. 3s has only one possible orientation because it is an s orbital. 3p has got 3 different orientations, that are, they are 3px, 3py, 3pz, and 3d has got 5 different orientations, 3dxy, 3dyz, 3dzx, 3dx square minus y square, and 3dz square. So, 1, 2, 3, 4, 5, these are 5 different ways, right. So, if I count the number of orbitals corresponding to n equals 3, I would see from 3s I got 1, from 3p I got 3, from 3d I got 5 orbitals. In total 1 plus 3 plus 5 is 9. So, I saw that when n equals 3, there exist total 9 orbitals. So, we can have a general rule as to say that for principal quantum number n, there are n square number of orbitals. So, when n is 1, there is only one orbital. What is that? 1s. When n is 2, there are 4 orbitals. What are they? 2s, 2px, 2py, 2pz. When n is equal to 3, there are 9 orbitals, and who are they? These are the orbitals that we wrote down here. So, we saw 3 different quantum numbers: principal quantum number, orbital quantum number, and magnetic quantum number. We saw that principal quantum number n is the leading quantum number which decides what are the possible values of L, and in turn L decides what are the possible values of M. With using n, L, and M, the 3 quantum numbers, we can go up to identifying the orbital or the house of the electron. But then there was something else that is called spin. It turned out that electron has an intrinsic property which is known as spin. By intrinsic, I mean that it is inherent to the nature of electron. You cannot separate spin from electron. If there is an electron, there has to be a spin. The spin is inbuilt in electron, and therefore, we have to take into account of the 4th quantum number, and that is the spin quantum number. So, together with n, L, and M, the 3 quantum numbers, when spin quantum number comes into play, we uniquely can identify a particular electron. This is what we are going to do next, the spin quantum number. So, our fourth quantum number is a spin quantum number. As I said, it turned out that each electron has a spin associated with it, and this spin quantum number is denoted by ms. And if principal quantum number n said about the size of the orbital, azimuthal quantum numbers talked about the shape of the orbital, magnetic quantum number talked about the orientation of the orbital, the spin quantum number talks about the spin orientation of the electron. Remember, when we discussed magnetic quantum number, we said that magnetic quantum number signifies the orientation in space of the orbital, the orientation of the orbital in space, in x axis, y axis, z axis, or within x y or on the x y plane or on y z plane, so forth, so on and so forth. But spin quantum number talks about the spin orientation. It is not spatial orientation, it is spin orientation of an electron. There are only two possible values of possible spin orientations. There are only two spin orientation for electron. They are given as ms value of plus half or minus half. They signify up spin or down spin. They are also called as alpha or beta. So, these are the two spin orientation of an electron. So, to summarize, we discussed about n, l, m, ms. The principal quantum number which talked about the size, this talked about shape, this orientation, this is spin orientation. N can be 1, 2, 3, so on and so forth. L can go from 0, 1, 2 till n minus 1. M can have value minus L plus 1, 0, L minus 1, L, and ms can have plus half or minus half. These are the quantum numbers that are used to uniquely identify an orbital or to uniquely identify an electron. Since orbitals are the place where electrons are found, we will now discuss little more about the shapes of the orbitals. If you remember, we obtained these orbitals by solving the Schrodinger equation H psi equals E psi, where the wave function psi are essentially the orbitals, and we saw that to identify an orbital we require a few quantum numbers. So, the wave function therefore is a function of n, l, m. These three quantum numbers are there in this wave function. So, this simply means wave function depends on L, m and m. So, if you have different n, l or m, you will have a different value of the wave, different form of the wave function. We got to know this. We also know from Born's hypothesis that the wave function itself, we call it orbital, but it does not have a physical significance. What has a physical significance is the square of the wave function, the psi n l m square. So, this tells us the probability density of the electron at a given point. This is important, because at a particular point you have a particular value of this wave function, and the square of it is actually the probability of finding that electron at that point. All right. The wave function, of course, as I said, the wave function contains the information about the position of the electron that you are interested. So, the position of the electron, how can I signify the position of the electron? Of course, I have to tell about that where it is located, its x value, its value in the x axis, y axis, z axis, then only I can spatially in the space I can pinpoint the position of the electron. So, I can have to define the position, I can have r, which is the position of the electron, as a function of x, y, z. This is given in Cartesian coordinate. Equivalently, what happens is that it was found that it is easier, since the electron actually goes around the nucleus in a circular path. So, it turned out that if we use another coordinate system instead of Cartesian, if we use spherical polar coordinate, then the solution of hydrogen atom problem becomes easier, and this is what I show you here. So, here the spherical polar coordinates are given, the relationship with the Cartesian coordinates are given. So, we have this x axis, y axis, z axis, the 3 axes, this is the origin. So, you can, since the electron is going around this sphere in 3 dimension. So, you can define one coordinate in the spherical coordinate, that is r, which is the radius of the circle, radius of the sphere, or you can define an azimuth angle, which is given as phi, and you can also have another angle which is which shows you this movement, it is clear, and that is given as theta. So, instead of x, y, z, my position, the position of the electron is given as r, theta, phi. This r is overall position, and this r is actually the radius of this sphere. So, I have now these 3 coordinates, r, theta and phi, using which I define the position of the electron. So, since the wave function contains information about the electron's position, so therefore, this wave function which requires NLM to be uniquely identified is a function of r, theta and phi. This is radial coordinate, these two are two angles. This wave function, this form of wave function can also be written down as product of two wave function, which contains one radial part, which is given as r and l, multiplied by an angular part which depends on theta and phi. So, this is the total wave function which depends on r, theta and phi, and is signified by 3 quantum numbers n, l and m. And I am now, what we are showing you is that we have broken down this wave function into 2 different components. One is first term depends only on the radial part. So, this is the radial component. The second part depends on theta and phi, that is called angular component. Right. So, it is radial component, angular component. The radial component is it is sufficient to use n and l to define them. The leading quantum number is n. For angular component, we have 2 quantum numbers l and m, and the leading quantum number is l, the azimuthal quantum number. So, this is the definition of the wave function in the spherical coordinate. So, we must appreciate that the wave function depends on the radial part and the angular parts. Now, the wave function square gives you the probability density. There is a special term that we would need here, is while the orbital the square of the wave function tells you the probability density, when the wave function is 0 or the probability, when the wave function is 0, the region, sometimes what happens, there are some region in the space, the region where your wave function is 0, and therefore, the probability vanishes. If probability vanishes, what does that mean? That means that in that region you do not expect the electron to be present. The probability of finding the electron at that place or that point or that region is 0, and when that is the case, we call that region as node. This region, I am intentionally using region, it can be a point or along a line or along a plane or along a surface, whichever. So, whenever the probability vanishes exactly, so the wave function is 0 and therefore, the probability is 0, we call that node. Now, you look at this wave function. So, we will get a node if this wave function becomes 0. This wave function psi has two parts, one is radial part, another is angular part. So, how can this wave function be 0? It can either be 0 when the radial component is 0, or it can be 0 when the angular component is 0. So, either this can be 0 or this can be 0. When the angular component is 0, that is again the node, because the wave function vanishes. When angular component is 0, we call that angular node. When the radial component is 0, we call that radial node. So, this 0, when the radial component is 0, this is radial node. When this angular component is 0, then we call it angular node. Now, we will discuss about what we can know about this radial and angular nodes. Let us first discuss about the angular nodes. Where y L m, which is a function of theta and phi, is 0. All right. The leading quantum number is L here. So, let us say when L is 0, we know when L is 0, what kind of shape do we get? We get a spherical shape of the orbital. When it is spherical shape, you see that no matter what value of theta or phi you take, since it is a sphere, you always have that probability density. So, when L is 0, you do not have any angular node, no angular node, or here we will count number of nodes that are angular. When L is 0, there are 0 number of angular nodes. When L is 1, we know the shape is like this. If you look at the px, py, pz orbitals that we have already shown, what you see here is that the 3 p orbitals, px, py and pz orbitals, the lobes you can identify, and what is shown here is a plane, the probability density becomes 0. So, that means on this plane that is highlighted here, on this plane you have no chance of finding the electron. So, the electron can either be in this side or this side, but not along this plane. So, this is called a nodal plane. So, this plane is coming because the orbital has a particular shape. You can see with px, py, pz, they all have one nodal plane each, and that is coming because of the angular component is 0. So, in this plane, the y L m, this part of the wave function becomes 0, therefore, you see this node. So, number of nodes for p orbitals is, you can see 1 in each case, px there is one plane, py there is another, pz there is another. So, the number of angular nodes are is 1 for p orbitals. When L is 2, we know the shape is double dumbbell, and I can show you another figure. Here you can see dxy, dyz, dzx, dz square, dx square minus y square, and you can see, since it is a double dumbbell, you can define two different planes along which the wave function or the angular component of the wave function vanishes. As you can see, in each of these d orbitals, there are 2 angular nodes. So, in d orbitals, you got 2 angular nodes. So, we can in general write number of angular nodes is equivalent to the value of L. So, the value of L determines how many angular nodes are there, how many regions where the wave function vanishes because this component of the wave function is 0, and the answer is L. If L is 0 for s orbital, there is no angular node. For p orbital, there is one angular node. Therefore, d orbital, there are two angular nodes. And next we discuss about the radial nodes. The radial part of the wave function depend only on the radial coordinate r, and this is 0. We will say that when does this component RNL or the radial component of the wave function becomes 0. We will first look for s orbitals. For s orbitals, what I am showing you here is the wave function. So, this the radial component of the wave function. In the x axis it is r plotted. The three figures that you see here are, one is for 1s, the other is for 2s, third one is for 3s. In each of the cases, the angular part is the same. This is given as s, they are all spherical orbitals. What I am showing you here is the radial component as a function of r. This r is the distance between electron and nucleus. So, this is my nucleus, this is electron, and this is the distance. When you look at the wave function, the radial component of the wave function for 1s orbital, you see this is the shape of the plot. You see that it exponentially decreases. When you look at 2s, you see the curve goes like this. I am retracing the curve. You see at one point of time, at one distance of r, at a certain distance of r, this wave function, the radial component of the wave function, it becomes 0. This is the x axis at 0. So, at one value, at this value r, at this value of r, the wave function is 0. So, that means at this value of r, the probability of finding the electron in the 2s orbital is 0. But as you go at higher values of r, you see the wave function has some negative value, but when you square it, when you calculate the probability of course becomes positive. So, at only one point, at one value of r, you saw that the probability does not exist. So, below that value of r, you have the chances of finding the electron. After the value of r, after that value of r, you again have the chance of finding electron. So, between while going along r axis, we get a point, get a value of r where there is no probability distribution. Below that value of r and after that value of r, we get probability distribution. That means, at that point of time, at that point of value of r, there exists a node, and this node is a radial node. So, we saw in one s orbital there was no such radial node. In 2s orbital, we saw one radial node. When I look at 3s orbital, this gives an interesting picture. What does it show? Let me retrace this curve. When I am drawing this asymptotic region at very large value of r, I am not making it 0, they do not exactly become 0, they just tend to go to 0, just very slowly they decay. So, I see again there is a sharp decrease in the wave function, and therefore, the probability as r goes on, but at again one value of r, there appears a radial node, and then again the wave function is non-zero. So, therefore, the probability is finite, and again at one more value of r, the probability is again 0. So, therefore, I get two nodes, two radial nodes in 3s orbital, one radial node in 2s orbital, and 0 nodes in 1s orbital. So, even if I have these 3 orbitals who have azimuthal quantum number same, they have same shape, S shape, spherical shape, I see 0 node or 1 node or 2 nodes. I can show that in another way. What I am plotting here in this picture is in the y axis, you have RNL square of it multiplied by r square, and this is the in x axis you have the distance here. This is called radial distribution function. This is the definition of this, but we can actually go through the results. When I look at this picture, I see that for one s orbital, the radial distribution. So, this is the square of this wave function. So, that means, if this was the radial component of the wave function, I have already taken the square. So, the plot that I am showing you signifies the probability of finding the electron at that value of r. So, for one s, the radial distribution function has this kind of shape. What do you see? You see a maximum probability at a certain value of r. Below that value of r and beyond that value of r, the probability decreases. If I show that in a different way, this is how I am showing. This is the distribution, electron distribution when the electron is in 1s orbital. You can see it is spherically distributed. So, it is a sphere with a certain value of r. Now, when I go to 2s, since the radial wave function look like this when I take a square. So, I see first it goes like this, and then I have this point which is a node. So, the probability density becomes 0, and beyond that again I see an. What does that mean? When I plot in this way, I see that in the center there is a density, probability density. This central sphere identifies this region, and the sphere beyond that, the second sphere that you can say is due to this probability distribution. And in between there are two spheres, there is a region where the electron is not found, and that is called a node. So, the white region that you see in this picture is a radial node. So, this is in 2s. So, you have got one node. When you look at the 3s, the radial distribution function has now 3 peaks. You can find this out, because there are two places where the wave function becomes 0, and therefore, there are two places where this probability density becomes 0. That means, there are nodes, and this is shown in this diagram this way. So, the inside component, the internal component sphere is due to this, the next sphere is due to this, and the last sphere is due to this. So, there are 3 concentric spheres, each separated by a region of space where the electron is not found. So, in this case you can see there are 2 regions of space where there are radial nodes, and so therefore, there are 2 radial nodes. Now, we will discuss about the radial nodes for p orbitals. Again, radial node is obtained when the radial component of the wave function vanishes. I have 2 pictures here. The picture in the right hand side shows the radial component of the wave function for a 2p orbital, and the left hand side picture shows the radial component of the wave function for a 3p orbital, and the x axis is again the distance between electron and the nucleus. So, when the electron is in a 2p orbital, the wave function has this behavior. You see, the radial component does not show any node. What you see here at r equals 0, what does that mean? That in case of one s orbital, in case of any s orbital, there was always a finite probability of finding the electron on the nucleus. However, when it is a p orbital, this probability is always 0. So, so this is not a node, this is actually a result from one limit when r goes to 0, and again similarly at very large value of r, this asymptotically goes to 0. So, in this case you see the radial function, radial part of the wave function has no nodes. So, this has got 0 nodes, and in case of 3p orbital, so the wave function looks like this, and how many nodes are there? You have to find out how many places this function crossed the 0 axis, and you can see there is only one point where it found. So, there is only one radial node in case of 3p orbitals. So, we saw that 2p orbital has no radial node and 3p orbital has one radial node. We will now try to generalize about the number of radial nodes. Let us first outline what we saw. We saw that for 1s orbital, number of radial nodes, here I will write number of radial nodes. For 1s orbital I got 0, for 2s I got 1, for 3s I got 2, for 2p I saw 0, for 3p I got 1, right. This is what we saw. Now, we can have a general definition as to number of radial nodes that an orbital will exhibit is given by n minus L minus 1. All right. Now, using this relation we will try to find out number of radial nodes in a few more orbitals. Let us say about 4p orbitals. In case of 4p, n is 4. So, n is 4, L is 1 minus 1 and again minus 1. So, 4p orbital will have 2 radial nodes. What about 3d? In case of 3d, you see n is 3, d orbital signifies L value 2. So, 3 minus 2 minus 1, this is 0. So, 3d orbital has 0 radial nodes. 4d will have 4 minus 2 minus 1, which is 1, and 4f orbital will have 4 because of n minus L, since f is the azimuthal quantum number which corresponds to the quantum number 3. So, 4 minus 3 minus 1, which is 0. So, this way we can calculate the number of radial nodes. If you remember, we found out that number of angular nodes was equivalent to L, right. So, number of radial nodes is n minus L minus 1 and number of angular nodes is L. So, total number of nodes is n minus L minus 1 plus L, which is n minus 1. This is the total number of nodes only depends on the value of principal quantum number. Our next point of discussion is boundary surface diagrams. Now, when I solve the Schrodinger equation of hydrogen atom, I get 1s orbital, I get 2s orbital, I get 3s orbital. The square of those wave functions are essentially the probability distribution. So, probability distribution means is that how many times I will find the electron at a particular value of r. What I am showing you here is a dot diagram. Each dot signifies that there exists the electron was found at that point of time. So, you can see that in this first picture, which is for 1s, this is for 2s, this is for 3s. In 1s you see a single sphere, but then you can also see that you cannot actually identify the sphere within which all possible locations of electrons are denoted, because you see here I have a dot, here I have another dot, but most of the dots are concentrated in this place. If I look here 2s, I see this in this orange color. I mean, these colors are actually for illustrative purposes, they do not have any other significance. I see when I look at 2s orbitals, I see some dots, each dot corresponds to that I found the electron at that point of time. This is the meaning of the dot. So, I see so many orange dots concentrated at one place, and then there is a gap where you can see the white space here, and beyond that again I again start finding the electrons, and this time they are given in green color dots. So, I see that electrons are present here, and then again the electrons are present here. Again I cannot really define a sphere, a circular shape within which the electron location will be found. Again similar story, if I go to 3s orbital, I see the central region and then another peripheral region, and then there is a gap and again some more dots. So, this is a this is the typical situation where I face problem as to what can I do about it. Now, when you look at this kind of situation, then you would ask, how did I get this a particular value of r for 1 s? How did I get these 2 spheres? How did I get 3 spheres for 3? The answer to that is that we try to estimate, we try to make sure that at least 90% of the probability density should be accounted for. So, it says that the radius of this 1 s orbital can be up to that point, up to which the region explains or accounts for about up to 90% of the probability density. So, you can see I can start from the center, I can keep on going and finding out the net probability, and when I see that okay, I have already accounted for the 90% of my experiments, the results from my experiments, then I say okay, this is all right, I am happy with this. So, this is the boundary surface diagram. So, then I can bound the surface at the region where I found 90% of the electron density. Similarly, when I look at the 2 s orbital, I start from the nucleus and I go on, and then I see at this point I have accounted for 90% of the electrons location. So, I say okay, this is my bound region. So, this becomes the boundary surface diagram for 2 s, and similarly for 3 s I do this. The boundary surface diagrams help us obtain the pictures that we showed. For example, the px, py, pz orbitals that I showed you earlier, you see these lobes. So, the lobe actually indicates I am the size of the lobe will be determined by the fact that within this region 90% of the probability density should be accounted for. This boundary surface diagram is a very useful tool to discuss the orbital shape. So far we have discussed the orbitals of the hydrogen atom. If you remember, we got these orbitals by solving Schrodinger equation, which is h psi equals E psi, where h was the Hamiltonian, the psi is the wave function which we call orbitals or atomic orbitals, and E is the energy. When we started solving Schrodinger equation, we said that the only known quantity we have is the Hamiltonian, the operator. What is unknown is the wave function and also the energy. By solving Schrodinger equation, we get the wave function which we have discussed so far as orbitals, and now we will spend some time in discussing about the energy that we get corresponding to those wave functions. Let us look at the energy. So, we started from h psi equals E psi, we discussed about the orbitals, and now we are going to discuss about this energy. So, by energy I mean energy of the orbitals. We will break our discussion into two parts. First, because there is an interesting story here. First, we will discuss about the energy of the orbitals for hydrogen atom. For hydrogen atom, and this discussion is also valid for all hydrogen like atoms. What are hydrogen like? If you remember, Bohr's atomic model was also applicable to all single electronic spaces. So, they are all single electronic spaces and we call them hydrogen like, He2 helium helium plus, lithium 2 plus, and so forth. Helium plus has 1 electron because helium has 2 electrons and I removed 1 electron. So, helium plus has 1 electron, lithium 2 plus has again 1 electron. So, they are all called hydrogen like systems. So, when I solved the wave Schrodinger equation, I got psi n l m. This is the wave function that I got and we discussed about it, and then I got the energy, and for hydrogen atom the energy only depends on n, depends only on the principal quantum number. it does not matter what value of L or M is, as long as N is given, there is a fixed value of energy. This is what the result from for hydrogen like systems are. So, let us find write down the wave functions that we have already discussed. So, psi NLM, so I will call it psi 1s, then I will have psi 2s, then I will have psi 2px, psi 2py, psi 2pz. So, NLM you can find out 2px means n is 2, L is 1, M is not exactly identifiable, but either -1 or 0 or +1. Then I can have psi 3s, psi 3px, psi 3py, psi 3pz and so on and so forth. Each wave function corresponds to an energy, right. This is what the solution of the Schrodinger equation said. So, this energy can be E1s, this is E2s, E2px, E2py, the energy corresponding to 2pz orbital, energy corresponding to 3s and so on and so forth. The solution for hydrogen atom showed that this is how the solution looks like. E1s has the lowest energy, then comes E2s, and the energy of E2x is exactly equivalent to the energy of E2px, which is E2py, which is E2pz, because as we discussed, the energy only depends on the principal quantum number n. All these 4 orbitals have same principal quantum number, that is n, and similarly E3s, which is again equivalent to E3p x, y, z, and it will also be similar to E3d x, y, y, z, z x, x square minus y square or z square. So, here you can see 1 orbital from 3s, 3 orbitals from 3p, 5 orbitals from 3d. So, total 9 orbitals have same energy. So, let us call this energy as E3. So, there are 9 different orbitals which have same energy, and here I see 1, 2, 3, 4 different orbitals have the same energy, and let me call it E2. And here for 1s there is only one orbital which has got that energy, and it is E1. When we see that there are more than one wave functions, psi 2s, psi 2px, psi 2py, psi 2pz, that 4 different wave functions, but they carry all of them they carry the same energy, we call these energy levels as degenerate. That means they are the same, they have the same energy. And since there are 4 energy levels which have same energy, so we call this situation as 4-fold degeneracy, and this situation as 9-fold degeneracy. So, third energy level of hydrogen atom is 9-fold degenerate. The second energy level of hydrogen atom is 4-fold degenerate, and the first energy level of hydrogen atom is non-degenerate or simply single-fold degeneracy. Now, we will talk about the second case for multi-electronic systems. For single electronic systems like hydrogen, we had the wave function psi NLM, and here also we have the same wave function, but here the energy value depends on n as well as L. So, energy value depends on n and L, but it does not depend on m. Okay. So, what do we have? Let us write down the orbitals that we know. So, 1s, 2s, 2p. So, I am not writing down now 2px, 2py, 2pz, because I already know that the energy does not depend on m. So, then 3s, 3p, 3d, I have 4s, 4p, 4d, 4f. These are the different orbitals that I got. I know their n value and L value, and I know their energy actually depends on n and L. In fact, the energy depends on their n plus L value. So, what we will do is now write down the n plus L value for all these orbitals that I wrote down here. For 1s, n is 1, L is 0. So, this is 1. For 2s, it is 2. For 2p it is 3, because n is 2 and p is L is 1. So, this is again 3. For 3p it is 4, for 3d it is 5, 4, 5, 4d is 6, 4f is 7. You can do that easily. Now, what we know is, or what we found out is that energy increases with n plus L value, right. Now, if we want to write down the energy levels in increasing order, this is how it will be. The lowest value of n plus L is because of 1 s. So, this is the lowest energy E 1 s. Its energy is less than, what is the next value of n plus L? That is 2. So, that is because of 2 s orbital, and what is next one? That is 2 p, and then you see both 2 p and 3 s, they have the same value of n plus L. When they have the same value of n plus L, the lower the value of n gets the precedence or has lower energy. So, then comes E 2 p, E 3 s, then energy is E 3 p. We have to be careful here, because 3 p has 4, 4 s has 4. So, the next orbital will be E 4 s, and then 5, you will have to look again, be careful, 3 d and E 4 p. So, the energy ordering is following the value of n plus L, and when there is same value of n plus L, we will say that we know that the lower value of n has lower energy. Just to remind you that at this point, that 2 p has threefold degeneracy, because it has 2 p x, 2 p y, 2 p z. There are 3 orbitals for the same energy. So, I will write down degree of degeneracy hash d. So, this is single fold degenerate 1, this has threefold degeneracy, this is 1 because 3 s, 3 p has 3, 4 s has 1 because it is s orbital, 3 d has 5 fold degeneracy, 4 p has 3 fold degeneracy. This degeneracy is only coming because of the magnetic quantum number, because we are not defining p x, p y, p z, 2 p x, 2 p y, 2 p z, they have the same value of energy. We will continue our discussion on the orbital energy of hydrogen atoms in our next class. We will see what other features are there in the orbital energies, and what physical intuitions physical insights you can obtain from the solutions of Schrodinger equation, and that is what we are going to discuss in our next class. Thank you.